Welcome to my lecture on hypothesis testing. Um, so hypothesis testing, the first thing that we're going to talk about is hypothesis testing on a population mean mu. Okay. This is slightly out of order from the presentation in your textbook, but that's okay. We will cover all the same material regardless. So hypothesis testing concerns a statement of the value of a population mean mu. And it's a statement of equality for H0 and a statement of inequality for the alternative. That's very important to keep in mind. The null hypothesis H0 is what's believed to be true about the population mean. And the alternative is what your researcher wants to prove. People often say that the null hypothesis is your status quo. So let's dive into an example right away. So an economist believes that we've entered a recession and that the mean wage of adults aged 18 and older has decreased from $16.25 an hour. To test this hypothesis at the 5% significance level, a sample of 30 individuals is taken, and it's found that a sample average of 14.9 an hour is found for the sample with a sample standard deviation of 375. What should the economist conclude? So we got a lot of things going on here, and let's just take a minute to back up. So first of all, our null hypothesis, what's currently believed to be the wage, is $16.25 an hour. That's our null hypothesis. Our alternative hypothesis is just that the mean wage is less than $16.25. It's not that it's $14.90, because the sample average is usually calculated after they form their hypothesis. Otherwise, that'd be what we consider cheating on your beliefs. Like, you have to form a hypothesis and then you collect data to substantiate that, not the other way around. You don't collect data to form your hypothesis. Okay. Now, this 5% significance level, that's going to be how we make decisions, and I'm going to talk more about that briefly. This 30 individuals comes from the data set, as do these two numbers, the sample average and the sample standard deviation. These are going to be needed to decide what to make a decision for the economist. Okay. So first things first, you want to state your null and alternative. So currently at $16.25, that's the statement of equality. Economist believes it's less, $16.25. Question that you might ask is, well, the economist has a sample and it was $14.90 an hour was the hourly wage. Why can't we just conclude, well, $14.90 is less than $16.25, therefore the alternative's true? That would be faulty logic, because the population mean is a statement of all individuals, whereas the sample average is just a subset of those individuals, okay, not the entire population. So what we'd like to know is, if I were to resample and take another average, I might not get $14.9 an hour. I might get $15.75. I might get $16.10 an hour. How small is too small? Or how big is too big is the question that we want to answer. When I take different samples, I'm going to get different answers for this $14.90. How much of a difference is big enough to conclude that it is in fact a different wage, that it has decreased, to decide in favor of the alternative, that is. So let's go back and talk about hypothesis testing. So there's various outcomes of hypothesis testing. So there's always a reality concerning the true population mean. It's not usually impossible to know what the reality is because it concerns the entire population, and it's very hard to sample the entire population. We have a decision. Our decision is here, is either to fail to reject H0 or to reject H0. Now we use the terminology fail to reject H0, but you can think of it as accepting H0 if you'd like, or concluding H0 is true. But in statistics we use the terminology fail to reject because it could be that the alternative is true and we just don't have enough data to conclude that the alternative is true. There's not enough evidence one way or the other. Now, there could be convincing evidence to reject H0, and you can think of this as accepting the alternative, if you like. Now, if we decide to fail to reject the null hypothesis, and that matches reality, that H0 is true, we've made the correct decision. That's a happy thing. But if we fail to reject H0, we conclude that H0 is true, but the reality is that the alternative is true. Well, that's a sad thing. We made what's called a type 2 error in that instance. Now, we could make a different decision. Our decision could be to reject the null hypothesis in favor of the alternative. If the reality is that the null hypothesis is true, that's again a sad thing. It's called a type 1 error. We made an error here. It's a sad thing. However, it could be that we reject H0 and the reality of H sub A is true. And we made the correct decision in that instance. We're going to make our decisions based off of the type 1 error that we're willing to subject ourselves to. In this instance, it's called the significance of the test, and that is 5%. That's what we're going to call alpha. Okay, so when we're making decisions, and we would expect that the null hypothesis would be false if the sample average is small. So we're saying here the population salary, hourly salary is $16.25, and we'd see evidence in favor of the alternative that it's less if the sample average is small, less than $16.25 an hour. How much less we need to use a calculation of probability to determine. So we associate how small a sample average is with the probability that the average is too small. That is, the data is unlikely to be true under the null hypothesis. And how small is determined by our significance level alpha. That's very important. Different level of alphas will lead to different decisions potentially. Okay. So the key to making our decision concerns the sample average x bar, and it leads us to this key statistic that we saw last time. Okay. Now, one of our assumptions is that data is independent, and the data is normally distributed or have a large enough sample, 30 or more. If you have exactly 30, that's okay. 30 works. Okay. When you make a decision with hypothesis testing, it depends on the form of your alternative. There are 3 forms of the alternative hypothesis. This one right here is that the alternative is less than some number, in this case 16.25. And we're going to reject if the sample average is in the rejection region, if it's less than some value r. And notice alpha, that's the significance level. It's entirely in the lower tail. And it's in the lower tail because we'd expect it to be less, the sample average, would be less than the mean under the alternative. Okay. Now, here the alternative is greater than some number, and our rejection region is going to be if the sample average is bigger than the average, mu. And the significance level alpha is entirely in the right tail here. Now, there's a third form of hypothesis testing, which is that mu is not equal to some number. It's unknown if it's greater than or less than, only that it's different. And here, there's two rejection regions. They're symmetric about the mean. So one is to reject the null hypothesis if it's bigger than some number or less than some number. That number is the plus or minus of it. And here only alpha over 2 goes in the left tail and the right tail. So there's two rejection criteria for this form of the alternative. Let's get back to the problem we discussed with the economist. And the first thing you're going to do is you're going to name the variable. So the first thing is to write down the null and the alternative. We've discussed that. So the economist believes that it's decreased. We're going to write down information given in the problem. We know the sample size, therefore we know the degrees of freedom is 1 less, 29. We know the sample standard deviation, we know the significance level, and we know the sample average. Okay, well, we're going to make a decision, and this is the critical value method that's discussed in your book. There are several other methods. Okay, and in this method, we're going to reject the null hypothesis if the odds of observing the data under the null hypothesis is less than alpha. That's the amount of risk you're willing to take for a type 1 error. In this case, it's 5%. And we're going to base our decision based on the sample average, because after all, that's what estimates the population average. Okay. And the rejection criteria depends on the alternative HF. So remember, there's 3 forms of it. So here, this is our form. Now, we're going to have the less than or equal to in our hypothesis testing. Because our alternative is less, that inequality there is less from our alternative. That comes from one of our 3 forms of hypothesis testing. We said we're willing to take on a 5% probability of a type 1 error. So that's where that 0.05 comes from. Okay. And our goal is to determine the value of the region R that corresponds to the rejection region. Okay. Now, I know I have the sample average here, and I can do both sides to the equation and not change probability because they're equivalent statements. So I'm going to subtract by that mean, and I'm going to divide by the standard deviation over root n. Now, this mu comes from the null hypothesis. That null hypothesis is 1625. So that's where this number, 1625, comes from. The 3.25 comes from the sample standard deviation. The n is the sample size. I know that this quantity right here is exactly a t-distribution with 29 degrees of freedom. Now, one thing you should ask is, where do I get this minus 1.699? Well, remember, I have a t-distribution with 29 degrees of freedom, and I want 5% probability in the lower tail. Okay, so I'm going to use an online calculator. Here's your hypothesis testing homework. I'm going to use this link right here for the t-distribution. I have a lower tail because that's the form of my alternative, and I want 5%, 0.05. I have 29 degrees of freedom, and I'm going to execute. Now, the value that it gives me is minus 1.699. That is exactly, this number is exactly the number that I'm using here, minus 1.699. Now, I want to determine my rejection region. I know all three forms of this equality are true, so I'm just going to set this number equal to this number and solve for the region R. So I set these two equal, I clear the denominator, and I move 16.25 to the other side. That gives me this. That's $15.2 an hour. Since I observe a sample average with 30 observations is 14.9, is less than the 15.2, we reject the null hypothesis at the 5% significance level. If my significance level was different, it might affect my conclusion. Okay? So our conclusion is to reject. Let's do another example. So in this example, an exercise scientist believes that in recent times, the mean amount of time spent exercising has changed from 40 minutes a day. It doesn't say how it's changed. So right now, the status quo, what's believed about the mean amount of time is that it's 40 minutes. That's our null hypothesis. The exercise scientist believes it's changed, he or she doesn't know how the mean amount of time exercising has changed. So that's why we get the 40. Now we're going to name the variable game and write down what we know. We know we have 49 observations, so the degrees of freedom is 48. The sample standard deviation is 28 minutes, so I get the 28 there. I have a 5% significance level over here. I have my value of x bar, but notice I have a two-sided alternative. That corresponds to this scenario right here. Okay, so since I have that scenario, I need to know alpha over 2, and that's that 2.5%. Now I'm going to do a hypothesis test here, and it's two-sided, just as I said, and it's symmetric rejection regions right here. So 5%, that's the probability that x bar is too small, it's less than minus the value, or x bar is too big, it's bigger than the rejection region. Because there's two ways in which it might not be equal. It could be too small or it could be too big. This is equal to, since it's symmetric, what's in the probability to the right is exactly the same as the probability to the left, and it's symmetric. I can just do this twice. The probability, the absolute value of x bar is bigger than that rejection region. So we get 2.5%. I just divide by 2 on this side of the equation. 2.5% is the probability the absolute value of x bar is bigger than the rejection region. Now, I can subtract the mean, divide by the standard deviation. I can use this fact that that's a t-distribution with n minus 1 degrees of freedom. Okay. So I get a t-distribution with 48 degrees of freedom, but remember the mean mu comes from the null hypothesis of 40 minutes. Null hypothesis 40 minutes right here. So I just plug in that number. I plug in the sample standard deviation, I plug in the sample size. So that's how I get this right-hand side here. And I also have this value of 2.01. That's the probability that t-distribution at 48 degrees of freedom is greater than 2.1. 2.01 is 2.5%. You might ask, how did I get that number? Well, I used the online calculator. Let's go back to it. So I want the upper tail, because the alternative is greater, to be 2.5%. There's 2.5%. And I have 48 degrees of freedom. We put it in there. And it gives us 2.01. So 2.01, that's the number that was put right here. And it comes from that online calculator. Now, I know that these two quantities have to be equal, so I set them equal to each other, and I solve for r. So r is going to be 40 plus or minus this 2.01. this plus or minus comes from this absolute value. So don't worry about this plus or minus. Just know that when you have a two-sided alternative, you're going to do plus or minus. So we're going to reject if x bar is greater than 40.04 minutes or if x bar is less than 31.6. Since x bar is 45, it doesn't meet this criterion. It's not greater and it's not less, so we fail to reject the null hypothesis. Okay. Now I want to point out these numbers correspond to a confidence interval, a 95% confidence interval, a 1 minus alpha percent confidence interval, and that we could just calculate a 1 minus alpha percent confidence interval. If x bar lies in the interval, we would fail to reject, if the mean mu under H0 lies in the confidence interval, we would fail to reject H0. If it lies outside of the confidence interval, we would reject H0. Now let's move on to one last example. Okay. And this example says the drug Lipitor is meant to reduce total cholesterol and LDL cholesterol. In clinical trials, 19 out of 863 patients taking 10 milligrams of Lipitor daily complained of flu-like symptoms. It's known that 1.9% of patients taking competing drugs complain of flu-like symptoms. Is there evidence to conclude that more than 1.9% of Lipitor users experience flu-like symptoms as a side effect at the 1% level of significance? So the first thing we're going to do is we're going to name the variables. But something's very different about this problem from the previous two. What's very different is that we're talking about the population proportion. So we want to know if the population proportion of Lipitor users suffer from flu-like symptoms at greater proportions than of all other competing drugs. So the null hypothesis is P0 is 1.9%, and we'd like to determine or prove if Lipitor proportion is greater than that of competing drugs, 1.9%. Other things that we have from the data is the sample size is 863. We have the sample proportion, which is different from the population proportion. So the null hypothesis and the alternative hypothesis are statements about the population proportion. Here we have a sample proportion, that's the 19 out of 863, and that's 0.022. We want to test this at the 1% significance level. I'm going to point out that this alternative hypothesis, it corresponds to a rejection region like this. We're going to reject if it's greater than the average. Okay. So we wrote down all the information that came from this problem, and that was the name the variable game. Okay. So this is different, just to reiterate, because we're testing a hypothesis concerning population proportions. Now we have something that estimates the population proportion, p hat, and we're going to reject if the sample proportion is bigger than some value, and that value corresponds to the probability of a type 1 error. Now our idea for doing this and reasoning is exactly the same as before, and that is if I was to take another sample, yes, p hat is 0.22 and that's bigger than 1.9%, 0.022, which is bigger than 1.9%. But if I was to take another sample, I might not get 19 individuals out of 863. So if I was to take another sample of 863, I might get 20, I might get 21, I might get 18. At what point is that conclusive enough to say that the drug Lipitor has a greater proportion than that of 1.9%. And we're going to do that according to probability. Our probability is going to be based on this 1% level. So our key to calculating probability here is this fact that when I take the sample proportion minus the population proportion and I divide by this quantity, I get a standard normal distribution. And I can only get a standard normal distribution if this criteria is met. So now let's use this key fact, that's really key, to calculate the probability and to also test the hypothesis. So one thing that I noticed, that criteria, 863 times 1 minus p times p, is 16, and I just plug in the values of p under the null hypothesis, and that's bigger than 10. So I'm good to use this fact right here, that that's standard normal. I have 1%, and I set that equal to the probability the sample proportion is bigger than some value. I can go ahead and subtract the population proportion and then divide by this quantity. I can do that on both sides. Remember, P0 is 0.019, so I just plug that in on this other side over here, and that tells me that I get a standard normal. I want the probability of standard normal to be bigger than some value to be equal to 1%. How do I get that 2.32 is what you might ask. Well, let me show you. I'm going to use an online calculator, but I need a slightly different one. So I'm going to use the normal distribution one. So I want the upper quantity, because that's the form of the alternative, 0.01. I have mean 0, standard deviation 1. So go ahead and execute that. And I'm going to get 2.32. That's the value I get. And that value of 2.32 comes from that calculation, that calculator. I know that everything has to be equal here, so this quantity has to be equal to this quantity. And so I'm going to solve for r. I clear the denominator and move the 0.019 to the other side. That gives me this, that's 0.02. If I saw a sample proportion of 0.029 or 2.9%, I could reject it. But since it's less, and I know I only reject for values greater than 2.9%, we fail to reject the null hypothesis. That's our conclusion. If this number were greater than 2.9% or 0.0298, I would go ahead and reject H0. But it's not, so I fail to reject. Okay. Well, thank you. That's all for hypothesis testing.